Testing.
Yeah.
Good.
You're good.
Oh, do you have it live right now?
Yeah, I like to have it live for a little bit, like 10 minutes before, just so.
Test 1, 2. Test. Test 1, 2.
Yeah, it's bright.
So let's jump into some problems. So we're going to start at the beginning and just kind of work our way through it. So how many of you have taken a look at this practice test and have tried some of the problems? Okay, that's okay. So I feel like these are some really good ones. You'll recognize some from past homeworks and also from his notes. But these are ones that I could definitely see him putting on the final. So for the first problem, this one was from the homework. It's from chapter 11. So you guys remember radial and transverse components? Kind of. So for radial and transverse, well, first off, this problem says, to study the performance of a race car, a high-speed camera is positioned at point A. The camera is mounted on a mechanism which permits it to record the motion of the car as the car travels on the straightaway BC. So we have to find the speed of the car in terms of b, theta, and theta dot. So we need to find v. And then it also says to find the magnitude of the acceleration in terms of b, theta, theta dot, and theta double dot. So find v, find a. So this is our knowns and unknowns. So now let's go ahead and write our equations that we have. So we know that the magnitude of the velocity, which is what we're looking for, is equal to the square root of the radial velocity plus the transverse velocity squared, right? The sum of the two. Do you guys remember what the radial velocity equals? So VR is equal to R dot. Okay, and then V theta is equal to R times theta dot. So for this problem, we're not given any sort of values. What we can do is from the geometry of it, we can come up with an equation for R. And once we have that, we can find the derivative of that with respect to theta to find VR, and then plug in the other stuff for V theta. So we also have equations for AR and A theta. So we know that AR, the radial acceleration, is equal to R double dot minus R dot theta, or sorry, that's R theta dot squared. And then A theta is equal to R theta double dot plus 2 R dot theta dot. So that's in terms of the radial and transverse, but what's another equation that we know for acceleration? What is acceleration the derivative of? Any guesses? Velocity, good. So we could also say that acceleration is equal to dv dt. So process-wise, what we're going to do is we'll find the velocity. Since we know that acceleration is dv dt, we can just take the derivative of that, and it makes it easier. So from the geometry, we could say that, so cosine of this angle is equal to b over r, right? So r is equal to b over cosine theta. Everyone see that? So once we have this, now we can start plugging stuff into our equations. So to find velocity, we know that VR is equal to R dot. So I need to find the derivative of that expression. So we're going to, this is, what is it, quotient rule? Low d high minus high d low over low squared. So we're going to say low, so VR is equal to cosine of theta times derivative of high, which is 0, minus high times the derivative of low, which is negative sine theta. But we also have to use chain rule because theta is itself a variable and it's dependent upon time. So this is times theta dot. So that's the trick with this one. And so this is all over cosine squared of theta. So this component is 0. And simplifying, we get b theta dot sine theta over cosine squared theta. So we found one component. Now we have to get v theta. This one is a bit more straightforward. So v theta is just equal to r times theta dot. So we have r. We know that r is b over cosine theta. And we're trying to get things in terms of theta, theta dot, and b. So it's just b times theta dot over cosine theta. That's it. Everyone good? So now we have to get this. We need the magnitude of this to find the total velocity. So we can say that v is equal to, I'm going to use these parentheses. We have b theta dot sine theta over cosine squared theta squared plus b theta dot over cosine theta squared. And that's all to the 1/2. Good? So from this expression, I'm going to try to simplify it. So what I'm going to do is I notice that in each of these terms, I have a b, a theta dot, and a cosine theta. So I'm going to say b theta dot over cosine theta. And then what I'm left with is actually I'm going to pull out a square of all of those. So this is b squared, theta dot squared, and then cosine squared theta, right? Because each of those terms is squared. So that leaves me with sine squared of theta over cosine squared theta plus 1. And this is all to the 1/2. And so this looks really horrible, but this expression here should look familiar. So we know that cosine squared theta plus sine squared theta is equal to 1. So I could rewrite that and say that, so if I divide everything by cosine squared, I get sine squared theta over cosine squared theta plus 1 is equal to 1 over cosine squared theta. Agreed? So I'm just simplifying. So I can take this expression here and plug in, so this is equal to 1 over cosine squared theta. So what this leaves me with is v is equal to, I have b squared theta dot squared over cosine squared theta times cosine squared theta, right? So I have cosine to the 4th of theta, and all that's to the 1/2. So if I take the square root, you end up getting v is equal to b times theta dot over cosine squared theta. But if I'm assuming that up is the positive direction, what should the sign of this be? Negative. So this is negative b theta dot over cosine squared theta. So now we already said that there's an easier way to find the acceleration rather than plugging it into these two equations. So we can just take the derivative of this. So I can say for part B that A is equal to dv dt. So that's the same as saying I have d dt of negative b theta dot over cosine squared theta. Good? So what we're going to have here is another quotient rule. So we have cosine squared theta, so low times the derivative of the high. So the only term here that has time, so with respect to time, would be the theta dot, right? So if I take the derivative of the top, I'm going to have negative b theta double dot. Agreed? So then I have minus negative b theta dot times the derivative of the low value. So that gives me negative 2 theta dot cosine theta times the sine of theta. So that's just chain rule. Good? He's not going to give you something this like conceptual. He'll give you values. And this is all going to be over cosine to the fourth of theta. So simplifying, you should get, so I see here that I have a b and a cosine, and then a b and a cosine. So I'm going to do this. Negative b over cosine squared theta. Sure. So I have negative b over cosine squared theta times, so for this term, I'm left with theta double dot. Then I have, so if I look at this term here, and I divide by the cosine squared, I end up with plus 2 theta dot squared times tangent theta. So it leaves me with the sine of theta over a cosine theta. Do you guys need me to show the steps with that? You guys good? So if I look here, I have a cosine theta over cosine to the fourth, so that reduces. If I pull the cosine squared out, then that leaves me with just one cosine. So I have sine over cosine, so I just wrote it as tangent. And so this is our final expression for acceleration. Any questions about this? So if you really wanted to, you could use the radial and transverse equations for acceleration and find it that way. But you would have to find the second derivative of the r value, and that's just a lot of work. So it's better to do it the easy way. You guys ready to move on? You guys are so enthusiastic. It feels like a Monday. Okay. What was that? I know. It's okay, we're almost done. You're almost done. So now we're getting into some chapter 12 stuff, and you guys might recognize this monstrosity if I pulled it down a little. So this one says, this was a homework problem, but I know it's a very difficult one, so it's a really good conceptual one to review. So it says block A has a mass. So step 1, knowns and unknowns. We know that MA is equal to 40 kilograms. We know MB is equal to 8 kilograms. And we're told the coefficient of friction between all surfaces, so we know mu S is equal to 0.2 and mu K is equal to 0.15. So this one says that P is equal to 0, so we just ignore that. So it says find the acceleration of block B and the tension in the cord. All right. So how do we know if these two blocks are actually moving? We know that the only forces acting on this are gravity and friction, right? So the only thing that's going to cause it to move potentially is the gravity. But is the force of gravity great enough to overcome the force of friction? Can we tell just by looking at it? No. So we have to do some lovely finagling with this problem. So before we start that, let's go ahead and look at the constrained motion for this. Let's look at the cables. So if I call this cable here a length of XA, so I have 1 XA, I'm going to call that 2 XA, and this one I'm going to call XB relative to A. So if I write this as an equation, I get 2XA plus XB relative to A is equal to some constant. Agreed? So if I take the derivative of this, I could say that 2VA plus VB relative to A is equal to 0. And I can say that 2 times the acceleration of A plus the acceleration of B relative to A is also equal to 0. So we also have equations for relative acceleration. So we know that the acceleration of B is equal to the acceleration of A plus the acceleration of B relative to A. So that's another equation that we have. So if I take and I solve for, so for this one here, I could say that AB relative to A is equal to negative 2 times the acceleration of A. Agreed? So if I take this, plug it into there, I can say that AB is equal to A plus negative 2 times the acceleration of A. And all this shows me is that AB is equal to negative AA. So we know that they move with the same magnitude but in different directions. So for the simplicity's sake, whenever I solve this problem, I'm just going to say A. And since I can assume which direction they're going to be moving in, I'm just going to draw them with respect to my assumption. Is everyone okay with that? So rather than plugging in multiple variables, if we know that these have the same magnitude, let's just call it A. So next we have to draw a free body diagram and a kinetic diagram. So I'm going to call, this was step 2, so step 3, FBD and KD. So if I draw a free body diagram for block B, so we're going to have our block on an angle. We know that we have a tension pulling it back up the incline. We have our normal. So I'm going to call this the normal between AB. So that's just like a contact force. I know that the mass, so we have MBG is acting straight down. And so if this thing is trying to move up the slope, which way is friction going to act? Down the slope, right? So I can call this the force of friction between AB. Good? And so I'm going to assume that this thing, so I'm drawing my free body diagram and kinetic diagram at the same time. I'm going to assume that this is moving up the slope. So there's my MA. Good? So now if I draw block A, so for block A, we know we're going to have a normal. We have MAG. So right now I'm just looking at A. So if I look back at this diagram, I have two tensions pulling it up, and then I have one that's going back the other way. So essentially, we just end up with one T pulling A up the slope. Let's see. So if A, I'm going to assume that A is going to go down the slope. So we can say that the friction goes up the slope. So I can say that I have, this is F, I'm going to call this force of friction. So that's just the contact between A and the surface. But I can't forget the normal and the friction that are in between A and B. So if I have this normal AB going up here, I have to draw it going down here. So that's just a contact force. And then I said that this friction was going down. So on this diagram, I'm going to draw it going up. And so as I said, we're going to assume that A is going down the slope. So you see what I mean by, for both of these, I just went ahead and drew in my assumed directions. And that accounts for the fact that they're going in opposite directions and they have the same magnitude. So that's all I did with that. It's just for simplicity. So we need to figure out if this thing is actually moving down the slope. So we're going to test equilibrium. So we're literally just going to look at statics for it. So if I'm seeing if this thing can overcome the static friction, which mu should I plug in? The static one, good. So now this is step 4. So I'm going to call this my EOE. So what I'm going to do is I'm just going to draw a line like this. So I'm going to look at B and I'm going to look at A separately. So I'm going to use tilted axes for these. Just sure thing. Good? So I'm going to say that the sum of forces in X equals 0, and I'm assuming that that way is positive. So going down the slope is my positive. And then sum of forces in Y equals 0, I'm going to say that going that way is positive. So I forgot, we need to draw in our angle. Well, actually, we're going to figure out if the angle of the slope is what can cause it to slide, right? So, for example, if I have like a flat surface, obviously it's not going to slide. But as soon as I start to lift it, at some point it's going to reach an angle where the friction is overcome and it's going to slide down the slope. So we're going to figure out if our angle is greater than, equal to, or less than 25 degrees. Sound good? So for block B, I have the sum of forces in X equal to, so I have negative T, I have plus FAB, so the force of friction between A and B, and then I have plus MBG, and is that angle going to be sine or cosine? Sine, good. So I have sine of some angle theta equal to 0. And so next I can say sum of forces in Y equal to, I have NAB, and then I have minus MBG cosine theta equal to 0. Good? So from this I can say that NAB is equal to MBG cosine theta. I also know that FAB is equal to US times the normal AB. And so we'll plug that in a minute. So let's go ahead and look at block A too. So if I say sum of forces in X, I have, so it's going to be negative T, then I'm going to have minus FAB. I have minus the force of friction between A and the contact surface. Then I have plus MAG sine theta equal to 0. So we know that the force of friction here is equal to mu s times our normal. So if I do some forces in Y, I have N minus NAB minus MAG cosine theta equal to 0. So I can say that N, and so here I know that NAB is equal to MBG cosine theta, right? So if I plug that in, I get big N is equal to MA plus MBG cosine theta. Good? So from my sum of forces in X equation for A, I'm going to solve for the tension. So I can say that the tension developed in the cable. So we know that between the two blocks, that tension's going to be the same, right? So essentially what I'm going to do is solve for tension for both of them and then equate them. Sound good? So I can say that T is equal to, let's see, I have negative FAB minus the force of friction, then plus mag sine theta. So I can start plugging in all of the variables that I have. So I can say that T is equal to negative mu s mbg cosine theta. So that's my force of friction of AB. So that was just mu s times NAB. So that's where that came from. Do you guys see it? So mu s times NAB. Then I have minus, so my force of friction, which we said was mu s times the big N. So that's going to be mu s, and then big N was equal to ma plus mb, right? So we have ma plus mb g cosine theta. And then lastly, I have plus mag sine theta. So that's one equation for T. From the other one, so bringing this one down, I can say that T is equal to, so I have T equals FAB plus MBG sine theta. We said that FAB was mu s times NAB. So I can say that T is equal to MBG, so I'm simplifying, times mu s cosine theta plus sine theta. Good? So now we can equate this. So I can say mbg times mu s cosine theta plus sine theta is equal to negative mu s mbg cosine theta minus mu s ma plus mbg cosine theta plus mag sine theta. This is a fun problem, right? So if we simplify this, are you guys okay if I just write what the answer will be? The only thing that we're missing from this, if you notice, the only unknown that we have is the theta. So if you solve for theta, you get theta equal to, what was that? But see, what we're trying to find, so that's like what I said with the ramp. So let's say I have something sitting on my phone here, and I start to lift it. Eventually it's going to reach an angle where it's going to slide down the slope. So what we're testing is this thing going to slide whenever it's 25 degrees? So we have to find a theta for it to slide, essentially. So what we find here is the minimum theta it needs to overcome friction. And so what you get for theta is 21.8 degrees. And so since our theta of the problem, which is 25 degrees, is greater than that, we can say that the blocks will slide. That was a lot of work just to do the next part of the problem. Are there any questions about this? Good? So the next part is going to be exactly the same, except now we're going to use the kinetic mu, and we're going to plug in our acceleration. So we know that this, so which direction is this thing accelerating in? Just the x, right? It's not accelerating in the y. If it were, it would be flying off of the system. So what we're going to, I need another piece of paper. So are you guys okay if I cover up the work for this? These solutions will be posted, but I need my diagram still. So what we can do now, so this is step 5. So we're going to say our sum of forces in x are going to equal the sum of forces in x effective. So that's essentially our acceleration in the x direction, right? And then our sum of forces in y will just equal 0, because we know it's not accelerating in the y direction. So if I look at block B, my equations are going to look very similar to before. So if I do, let's start with sum of forces in Y. So this is block B, and that's for block A. So for sum of forces in Y, I have NAB minus MBG cosine of 25 degrees equal to 0. So now we're plugging in the one that we're given in the problem. So this just tells me that NAB is equal to MBG cosine 25. So now if I do sum of forces in the x direction, that's going to equal, so in the way I have this drawn, remember I said that going down the slope was the positive direction. If I look at what I said for my kinetic diagram, I have acceleration going up. So I'm going to have to plug in negative mb times acceleration. Good? So I get negative t plus fab plus mbg sine 25 is equal to negative mb times a. Good? And so once again, same process for this. We're going to do the same thing for block A. We're going to solve for the tensions, equate them, and that'll give us the acceleration that we're looking for. And then once we find acceleration, we can plug it back in and get tension. So we showed through constrained motion that the acceleration of block B is the negative of block A. So they're equal but opposite. So for this one, if I solve for t, I get t is equal to mb. For friction, we're using mu k times the normal AB. So this is 0.15 times g cosine 15. Then I have plus g sine of 15. Then I have plus a. So what I did, just to explain, I know I did everything in one step, but I moved the MBA over from the right-hand side to the left side of the equation, which made it positive. Then I moved the negative t to the other side, so I just made everything positive. So that's my equation for tension. Yeah? You're right, thank you. Good call. I think I put 15 because mu k was 15. Thank you. So then if I look at block A, sum of forces in Y are equal to N minus NAB minus MAG cosine, oh, that got really messy, cosine of 25 equal to 0. So all that this tells me is that my normal, it's the same as before, MA plus MB G cosine 25. Then if I do sum of forces in X, so notice that I have the acceleration of A, or the acceleration going down the slope. So I can say that this is equal to MA times the acceleration, right? So plugging in the forces, we have negative T minus the force of friction minus the force of friction between A and B, then plus MAG sine of 25 is equal to MA times A. So we said that the force of friction is going to be mu k times the capital N, which we just found. We know that FAB was equal to mu k times the normal between AB, which we know that. So solving again for the tension here, we get T is equal to, so I'm going to pull out G, and so this is just me simplifying it. We get MA sine of 25 minus my mu k, which is 0.15, times MA plus MB times, sorry, that should be 2 MB. So we have MA plus 2 MB. If you have questions on how we simplified it, I can go over that, but I figure you guys just kind of want to get to the harder stuff. Then we have cosine 25, and then minus MAA. Everyone good? So we're going to take both of these equations and set T from the A equation equal to T from the B equation. So do you guys see, if I look at this, the only unknowns that I have, if I equate the two, is acceleration. So you guys, do you want me to just write what we get for acceleration? Please. So solving, you get the acceleration is equal to 0.9857 meters per second squared. And so for B, it's going like we said, and that's up the slope. And so now that we have that value, we can take it and plug it into one of the tension equations. And you get T is 51.72 newtons. Any questions about this one? Do you guys kind of see how the steps worked with it? It was kind of repetitive. Good? All right, you ready to move on? Some of you look done already. All right, so again, these solutions, they will be posted on my website afterwards. And I promise my handwriting looks a lot better on those. Also, so for those of you who really want the extra practice, I left all of my old practice exams and all of the solutions to those on my website. So feel free to take a look at any of them. Because topic-wise, he's taking, I believe he said 2 problems from each testing cycle. So for example, exam 1 was chapters 11 and 12, I believe. So he would give you 2 potential problems. One will probably be on 11, one will probably be on 12. You pick one of them to do. And so I believe there's going to be 10 total problems, but you're going to end up picking 5, is my understanding. You're going to have to do 1 from each testing section. So that's how he has it broken up. All right. So I believe you guys had a quiz on this problem. I know it was a homework problem. I'm pretty sure it was also a quiz. So this is a good one to go over. So this says a spring is used to stop a 50 kilogram package. So we know the mass is equal to 50 kilograms. So the package is moving down a 20-degree incline. So theta is 20 degrees. The spring has a constant K of 30 kilonewtons per meter. And is held by cables so that it is initially compressed 50 millimeters. So you guys remember for our spring equations, if we're looking at energy, then it's going to be x minus x naught, right? So our x naught for our spring is 0.05 meters. Then it says, knowing that the velocity of the package is 2 meters per second when it is 8 meters from the spring. So I can say V1 is equal to 8 meters per second when 8 meters away. What was that, 2? Thank you. It's already been a long day. So 2 meters per second when it's 8 meters from the spring, and neglecting friction, which is nice. Determine the maximum additional deformation of the spring in bringing the package to rest. So we know that V2 will equal 0. So we're told that it's going to go to rest. And then we have to find the X max. So we're finding the additional deformation of the spring. So how much additionally is it going to get compressed? So this was our knowns and unknowns. So my favorite step 2, free body diagram. So if initially our package is up here at 8 meters, and we know it's going to slide all the way down the slope, I'm going to set my datum at the initial spring position. So where the spring is at 0.05. Everyone good? So I'm going to draw a line right here. So my datum is my 0 point. So we know that this angle is 20 degrees and that this is 8 meters. And we don't know what this is. So if this is my additional deformation, I'm going to call this X. So that's what I'm going to look for. So I can also figure out like the heights of these. So do you guys see how we're going to start working with energy with this one? This one kind of lends itself to energy. Anytime I see something that's like up on a hill and I know it's sliding down a hill, I know there's a change in height. So I immediately think of potential energy. So I can say that this height here is equal to 8 times sine of 20. I know that this angle that's below the horizontal is also 20 degrees. So I can say that that height, is there a question? Okay, that height is equal to x times sine 20. Good? So we know that our equations for this we're going to say T1 plus V1 is equal to T2 plus V2, right? So we know that we have an initial kinetic energy. We know that our final kinetic is going to equal 0, right? So I can say that, so first off, which symbol represents kinetic, T or V? T, good. So we can say that T2 is 0. So initially, what was that? No, and we'll get to that. So for our initial potential energy, so we already said we initially have kinetic. For the final one, we don't have kinetic. For our initial potential, what do we have? We have gravity and we have the spring. So what is our equation for potential energy for a spring? Good. So I can say that I have T1, and then I can say I have V1 due to gravity plus V1 due to the spring, and that's going to equal my V2. So for my second position, what kind of potential energy, what kind of potentials do I have? So we're still going to have spring because that's the new deformation that we're looking for. What else do I have? So if this line right here is 0, am I going to have potential energy if it's below that line? Yeah, the height isn't 0. So we're going to have V2 due to gravity plus V2 due to the spring. And now we're going to start plugging stuff in. So we said that we know that the energy due to a spring is equal to 1/2 K times delta X squared. So, writing this all out, I'm going to write it down here so I have more space. For T1, I know I have 1/2 mv1 squared. Then for gravity, I have plus mg h1. So this is h1 I'm going to call that H2. Then I have plus 1/2 k x squared. This will equal, so kinetic is 0. My V2G will be mg H2. Then I have plus 1/2 k, I'm going to call this position x2 squared. So this, I'll change that to x1 squared. Good? So now we're going to plug everything in. So I have 1/2 times the mass, which is 50, times v, which we said was 2 squared, plus 50 times 9.81. Can everyone see that okay? So my height 1 is equal to 8 times the sine of 20. Then I have 1/2 times k, which we said was 20 kilonewtons per meter. So I have to make sure I plug in newtons for that. So that's going to be 30 times 10 to the 3. And then for my initial deformation of the spring, what do I plug in for that? What was that? Yeah, it's 30 kilonewtons per meter. What did I write? I'm sorry. I guess I saw 20 degrees. Like I said, it's been a long day and it's going to be an even longer one. If you guys want, I have a statics review tonight at 8. So, so for our x for this one, it's going to be the 0.05. So that's what the cables are compressing the spring at. So we have 0.05 squared. So that's for position 1. Now for position 2, so after it's come to rest, we have our mass, which is 50 times 9.81 times the height. So for this height, we're going to plug in negative x times the sine of 20. Everyone good with that? Yeah. So it's under our 0 point. So our datum, we said, was right there. Anything below that would be negative. Then I have plus 1/2 times my k, which is 30 times 10 to the 3. And then for that deformation, I'm going to plug in 0.05 plus x squared, right? So it's initially compressed 0.05. It's going to be compressed even more. So it's an additional compression. So just for your guys' sake, I will write out like the next line, and then I'll write out the answer. So you end up getting 1479.59 is equal to negative 167.76 x plus 37.5 plus 1500 x plus 15000 x squared. So you get a quadratic. So solving for it and then taking the positive value, you get x, so is equal to 0.269 meters. So that is how much extra that spring gets deformed to bring the block to rest. Any questions about this one? You guys good? Good. So full deformation would be the addition of it, yeah. All right. 3 down, 5 to go. So let's see. What else do we have? So, oh, by the way, chapter 14, I don't have any problems in here from chapter 14, but it's essentially just chapter 13 again. But that's where you have like all the collisions. Don't forget your equation for like E, the coefficient of restitution. So this is just, it's like chapter 13, but multi-particle. So it's same process. Now for some chapter 15 fun. I feel like chapter 15 is everyone's least favorite chapter. So, This one says, knowing that at the instance shown, crank BC has a constant angular velocity of 45 RPM clockwise. So I know, so step 1, knowns and unknowns. I know that omega BC is 45 RPM clockwise. So to convert that to radians per second, I multiply by 2 pi over 60. So that gives me 4.7124 radians per second clockwise. So there's my omega. It says that it has a constant angular velocity. So what does that say about alpha? 0, good. So we know that alpha BC is equal to 0. And it says find the acceleration of point A, so find AA, and find the acceleration of point D, so find AD. So for these problems, these are very systematic problems. So whenever I'm given an omega for a particular bar, I always start with that one first. So start with the one that you have the most known values for. So also some equations that we're probably going to use for this. We know that velocity is equal to r times omega. We also know that the magnitude of acceleration is equal to at squared plus an squared. So the tangential and the normal components. So for my tangential acceleration, what is that equation? That works, but what is it? Well, that's normal. So for tangential, the tangential one is very similar to tangential velocity. So it's r alpha, good. And then for normal, it's kind of like what you said, but we want to work with omegas for this. So it's going to equal r omega squared, but that's going inwards, so it's always directed in. So now, for crank BC, so since we're told omega BC, we're going to start with that bar. So drawing my free body diagram for it, I know that my omega is going that way, and that is 4.7124 radians per second. And we know that the velocity is going to act tangential to that. So there's my v, and this is vb. And this is point C, that's point B. And that's all that we have for that one. Then if I draw this, I'm going to try to use the same diagram. For acceleration, again, we said there's 2 components. So we know that there's my ABT, the tangential component, and then the normal component, which we say acts inward. So I have ABN. Everyone good so far? And then my radius for this, or my R value, is 4 inches. So for VB, I can say that VB is equal to 4.7124 radians per second times R, which is 4 inches. So that gives me 18.85 inches per second going up. So I found the velocity of point B. Now I can find the acceleration of point B. So we said that the tangential acceleration is equal to r alpha. But what did we say alpha was for this? Alpha is 0. So we know that acceleration of B tangential is 0. So all we have is normal acceleration. So I can say that ABN is equal to R, which is 4 inches, times omega squared. So that's 4.7124 squared. And that gives us 88 0.83 inches per second squared, and we know it's going inwards. So we started with the rod that we knew the most about, and we found velocities and accelerations on a point that we can then relate to the rod that we don't know anything about. Yeah.
The normal is that, and like if you put it inside the
Right. Right. So that is the total acceleration of that point, just like you said. So now if I look at rod DBA, so this rod is not a slant like this. So this is point D. I have point B, then I have point A. So we already found the velocity of point B. We know that this point is going up 18.85 inches per second. And I'm just gonna, so to keep the diagram simple, I'm just gonna put velocities on this one, and then I'll draw an acceleration one next. So, looking at point A, what kind of motion is it constrained to? Yeah, so it can only go up and down. So we know that velocity of A has to go up, right? And so looking at this problem, we can say, so if I were to try to draw an instantaneous center, do you guys remember how we would do that? So to get an instantaneous center, you take and you draw a line at the tail of your velocity vector, and you draw it perpendicular to that velocity vector. And then where those two lines intersect, that's your instantaneous center. But look at what happens if I do that for this one. They're parallel. So if they're parallel, then that means that our IC is equal to infinity. So our instantaneous center, it doesn't exist. It's at infinity. And so that means that this rod is only translating. So this thing is just, so it's at an angle, it's just moving up and down. It's not rotating, it's not doing anything else, it's just translating up. So what can we say then about the omega for this one? Omega would be 0, good. So if your instantaneous center is at infinity, we can say that omega dBA is equal to 0. So again, we only have translation, we don't have rotation. And so looking at this, if it's only translating, we can say that VA is equal to VB, which is equal to 18.85 inches per second going up. So we found the velocity of point A. Now we have to look at the accelerations of this one. So, redrawing my diagram. So at point B, we know that we had our normal acceleration going to the right. So that was 88.83 inches per second squared. For point A then, so our tangential acceleration has to move perpendicular to that rod. So this right here would be our A tangential. And then this one, so going towards the center, would be our A normal. And then, so we are asked for acceleration of point D, so I'm going to go ahead and draw that on here too. So for D, I labeled these differently than I did before, but instead of this being acceleration of A, I have this should be acceleration of A relative to B. Sorry, this is relative to B. And then this one here, this is acceleration of D relative to B, and that's tangential. So notice how I have it going the opposite way. And then that right there would be AD relative to B normal. Good? So right now I'm just drawing my diagrams. I know that this angle right here and this angle right here are both 30 degrees because that was given in the problem. Well, actually, no. So we can find that by the geometry of this. So if I call this theta, yeah, so that's 8, that's 4. Theta is equal to sine inverse of 1/2, which is 30 degrees. So writing out my relative acceleration equation. So this is what kind of motion does it have? So if I told you that something was translating and rotating, what would that be called? What kind of motion is that? It's called general plane motion, right? Oh, I thought I had to sneeze. We're all good. So general plane motion is the sum of translation plus rotation. So what I can do is I can say that, so if I'm looking at point A first, I can say that the acceleration of A is equal to the acceleration of B plus A relative to B. But we know that we have two components, right? So this is the same as saying AB plus AA relative to B tangential plus AA relative to B normal. So if we plug in our equations that we have for these, we said that acceleration of A, or acceleration of a point, yeah. Because there's a component that we don't know yet. So we'll get to that. But we have to break it apart. So essentially it's like back to static. So we need to resolve things into vector form. So we need to simplify it. So our normal component we know is equal to R times omega. So for this rod, this is rod dBA. And that's omega squared. But what do we say about omega dBA? It's 0. So our normal component is 0. So we only have a tangential component. But we don't know what alpha is. Can we just assume that alpha is 0? I'm going to go with no. And the reason is because we're looking at a particular instant. Just because at a particular instant they're both moving with the same velocity doesn't mean that something's trying to force it to rotate. So at another instant they may not be. So for example, like if this thing were to fall just a little and rod BC would be at an angle, then A and B would no longer be parallel. So this value is going to be R times alpha dBA. So writing this out into component form, we get, so we know that A can only move in the y direction, right? So I can say AAJ is equal to the acceleration of B, which we said was 88.83, and that's in the positive I direction. Then I have R times alpha, which I don't know. So our R value, what is our R value going to be? Good, it's 8. So it's the distance from point B to point A. So I have plus 8 times alpha dBA, but I need to break that into I and J components. So for my I component, if I'm looking at this, if I want the I, that's going to be cosine 30. So I have cosine 30I, and then for J, I have sine 30J. So taking this, I can solve for my alpha and my acceleration of point A. So if I look at my I components first, so I'm equating all of those components. So I have 0 in the I direction for A is going to equal 88.83 plus 8 times alpha dBA times the cosine of 30. So keep in mind, I didn't say it here, but for this one, I assumed that alpha was going in the positive direction, which means that it's going counterclockwise. Okay? So I was just assuming the positive. And so you'll see whenever you solve this, you get alpha dBA is equal to negative 12.821. Radians per second squared. And then if I look at my j components, I can say that acceleration of A is equal to 8 times alpha, which we said was negative 12.821, times the sine of 30. And so this tells me that the acceleration of A is negative 51.28 inches per second squared. So that means that A is actually accelerating downwards. So the velocity is going up, the acceleration is going down. So that means it's slowing down. Everyone good? So now that we've found, yeah. Yeah, so I assume that alpha was positive, which means that it's in the counterclockwise direction. So now for D, it's going to be the same exact process. So looking back at my diagram, I'm going to switch to the purple pen. So I can say that acceleration of D is equal to acceleration of B. And again, it's just the tangential and normal components. So I have plus AD relative to B tangential plus AD relative to B normal. For my normal component, it's going to be R times omega dBA squared. But again, what is that value? 0. So that goes away. And then for this one, we're going to have R times alpha dBA. So it's going to be the same alpha that we just found. So we can say, so we don't know, so point D is not constrained to a particular direction like point A was, right? So that's why I started solving for point A first. So point A, we knew it had to be in the Y. Point D, it's probably going to be in the I and the J. And so we'll see whenever we start to solve. So I can say I have AD is equal to AB, which is 88.83I. Then I'm going to have plus, so I have my R times alpha. So I have 8, alpha was negative 12.821. And then for my I and J components, so if I come up here and I look at my diagram, for my X component, it's going to be cosine of 30, but notice which direction it's in. Good. So the J and the I and the J are both negative. So I have negative cosine 30I minus sine 30J. So simplifying and solving for AD, we get AD is 177.65I plus 51.28J. That's in inches per second squared. And then if you were so inclined to, you could find the magnitude of this. So take the square root of the sum of the squares. That would give you, so if you did decide to do that, it would give you 184.9. And then if you did tangent to get the angle, you would get, this is at an angle of 16.1 degrees. Good? 184.9 inches per second squared at an angle of 16.1 from the horizontal. So that's if you were asked for like the angle that it makes. Any questions about this one? So just to review, the biggest, like the key thing with this, Start with the one that you know the most about, relate it to a common point between the two, and then just work your way from there. So I'm sure you guys remember, you have the ones that have multiple multiple rods. You just kind of work your way across the system. So you guys ready to move on? All right, let's do this. Here's another chapter 15 one. So this is one of our favorites, Coriolis. So this says the sleeve BC is welded to an arm that rotates about point A. So this entire thing is rotating about this point. All right? So it says it's rotating with a constant angular velocity of omega. And we're told that omega is equal to 3 radians per second in the I direction. So it's this thing is kind of flipping like that. Like, I don't know what it's doing. These are weird. In the position shown, the rod DF is being moved to the left with a constant speed of U is equal to 400 millimeters per second. So that is 0.4 meters per second, and that is in the K direction, right? So if looking here, so that rod that slides through the sleeve, it's moving in the K direction. Good? So we have this sleeve, that BC, which is welded at A, and then there's a rod that's sliding through it. So the rod is sliding with the velocity of 0.4 meters per second in the K direction. For the given angular velocity omega, find the acceleration of point D and the acceleration of the point of rod DF that coincides with point E. So basically, there's a point right here on the rod DF, and they want the acceleration of that rod. That's it. So it's just, the way they word it is really weird. So we're finding AD, and then acceleration of P on rod DF. And so I'm calling this point here, yeah, P, E, whatever you want to call it. If you want to call it point E, that works. Like I said, the way they worded that is really strange. So this is our knowns and unknowns. All right, next are equations. So we know that we're talking about acceleration. So we have our lovely long equation. So for acceleration of any point, we know that we're going to have 4 different components that we're going to look at. Do you guys remember what those 4 components are? Well, just what they're called in general. So we have normal, we have tangential, we have Coriolis, and then we have slip, right? So for our tangential component, that's just going to be omega dot cross r. So that omega dot, that's the same thing as having alpha. So that's just acceleration. Then for normal, I'm going to have omega cross r. Then for Coriolis, I'm going to have 2 times omega cross r dot, or v relative, whatever you want to call it. Then I have plus r double dot. All right, so now if we look at point AD, so we're going to use the same equation for both points. So the only difference between the two is going to be our r vectors that we use. Yeah, so that's the slip. So the only time where you would have slip is, let's say, if they told you that this rod DF was accelerating, or if it was decelerating at a rate of whatever, that would be slip velocity. So we're told that it moves at a constant rate, so what can we say about slip? Slip acceleration is going to be 0 for both of them. Yeah, well, I mean, they will just say, like, they'll say, so this one they say Rod DF is moving to the left at a constant speed of u equals 0.4. If they said it's moving to the left with a velocity of 0.4 and it's decelerating at a rate of 0.2, then that's whenever you would have slip. So for point D, so if I'm looking at point D, or just in general for this problem, we're told that we have an omega of 3 radians per second. In the problem, it says that it has a constant omega. So what does that mean about omega dot? 0, good. So omega dot, and we already said it, r double dot, those are both equal to 0. Yeah.
Why is it 0 in this case? Like, and then the test we just had, it was like omega 1 cos omega 2. Like, in all
That's if you have, so that's a really good question. So that's if you have two different rotations. So if this thing, so this one's rotating about the x-axis, but let's say it was also rotating about the y-axis, then you would have an alpha. You would have to do omega 1 cross omega 2.
is there like,
So yeah.
like a simple explanation, like, why? I mean, I'm still not like seeing it. I just remember it for the test.
Mhm.
But,
So the way that I would approach what you're saying is if you have multiple omegas for the frame, then that's whenever you would have omega 1 cross omega 2. And if you look at my last review, that's where I did a lot of problems like that. I think I had 2 on there.
I remember like in the review,
Yeah.
I don't know why it was, but I assumed it was 0.
Yeah, but it's because for the alpha, it's equal to omega dot, which is equal to omega dot oxy z for the frame. So that's like if the frame were accelerating. And then you're going to have plus the omega cross omega. So it would be like, essentially what this boils down to is if you say that the point itself has a total omega of omega 1 plus omega 2, which is what we were getting at before, then if you, whatever you call your frame, that's only going to have one rotation. So no matter what happens, this will end up equaling like omega 1 cross omega 2, because one component is going to be in the same direction, so it cancels.
They had like 1 omega cross
Mhm.
total. And then, yeah, just,
Yeah. So this one, we don't have to do that because it only has 1 omega. Really good question, though. And then, so for this one, we can say that our big omega is just that omega, which is 3i. Then for our r dot, so essentially the way I solve these is I always write this really long equation out, and then I go back and I find all the components that I need for that equation. So for r dot, we know that that is equal to our u, which is 0.4 in the k direction. And the last thing I need for this, what was that? What is r? Oh, I'm getting to that. That's what I'm about to talk about. So next we need RA relative to point D, or whatever you want to call it. So essentially, we go from the point that it's rotating about to the point that we're interested in for the acceleration. So we need RAD, and so for this one, that's going to be negative 0.12J, and then positive 0.3K. I don't know why I wrote it that way. Let's just chalk that up to being a long day. Okay. So we have every component that we need for this now. So now we can just start plugging it in. So, yeah, r dot is u. So that's why, like, I would memorize kind of, don't worry so much about the symbols that you have in this equation here. Know what each component is. Because another way you could see this is alpha cross r plus omega cross r plus 2 times omega cross u plus, that would be like u dot. So I mean, that's another way you could write it. So that's why I mean, like, know what each component is. So know that it's the tangential component, the normal component, the Coriolis, and the slip. Because if you know what each thing is, you won't get too tripped up on what the equation is giving you. So acceleration of point D. So we already said that the omega dot was 0. So that component's 0. So now I have my omega cross R A D. And then I have plus 2 times omega cross U, or cross R dot. See, there I go. I'm sorry. So plugging stuff in, we get, so that omega is 3I, and that's crossed with 3I, and then our RAD was negative 0.12J plus 0.3K. Then we have plus 2 times our omega, which is 3I. So you guys okay if I just write 6I for that? Good. So this is just 6I crossed with U, which we said is 0.4K. All right, so now we're going to use our IJK circle. So if I do this interior one first, I have I cross J, that gives me positive K. So actually another way that we could write this, do you guys remember that this part here is the same as saying negative omega squared times RAD as the vector? So that way we don't have to do any cross product. So let's do that instead. So it works out the same way. So I can say negative 3, and so this is just plugging in the magnitude of it. So negative 3 squared times the vector, which is negative 0.12J plus 0.3K. And then I have this other cross product. So I just have to do one cross product that way. Do you guys see that that's a bit easier? Sorry for switching it up in the middle of the problem. So if I say I cross K, that gives me negative J. So I have negative 6 times 0.4, which gives me negative 2.4J. So simplifying this, you end up getting acceleration of D is equal to negative 1.32J minus 2.7K, and that is in meters per second squared. Good? And now for the next one, the only difference between point D and then point AE, or point E, is that our R value is going to be different. So RAE is only going to be negative 1.2J. That's it. So we're just going down from A to point E. Is everyone okay with this? So our equation, it's going to look identical, except for the R value. So we get AE is equal to negative omega squared times RAE. And then we have plus our 6I cross 0.4K. So like I said, same exact process. Our R value is the only change. So we have negative 3 squared times negative 0.12J, and then that is minus 2.4J. So you get the acceleration of the point P or point E, whatever you want to call it, the acceleration of this thing that's like on the one rod is negative 1.32J. So if you notice, that's the same exact acceleration in the J direction for point D. For this problem, yeah. So it's linear acceleration. And that is in meters per second squared. Everyone good with this? I feel like this is a really good problem, so I would expect something similar to that on the exam. Ready to move on to chapter 16? 16, 17. So there are 3 more problems. I believe I can get through 2 more. So, how many of you would rather do, how many of you want to do a chapter 16 problem? Raise your hand. Okay. How many of you are like, I hate chapter 16, let's go over chapter 17 and 18? 1 person. How many of you really want to make sure we get to a chapter 18 problem? So are you guys okay then if we do the chapter 16 problem and then skip the chapter 17 one? Okay, so again, the solutions will be posted for this. The chapter 17 one, I'm okay with skipping because it's a work energy one, and I already showed you an energy problem. So it's a very similar kind of process. So we're going to go over the chapter 16 one and then chapter 18. Chapter 16 is my favorite chapter in dynamics. So, lucky you guys. So this says a 12-pound uniform plate. So, knowns and unknowns. I need like an abbreviation for that. So weight of the plate is equal to 12 pounds. So I can say that the mass of the plate would be 12 over 32.2, which gives me 0.3727. And that's in pounds, seconds squared over feet, or slugs, whatever you decide to call it. I don't like slugs. So it says that this plate rotates about point A in a vertical plane under the combined effects of gravity and the vertical force P. So notice in this problem that it's in a vertical plane. If it were in a horizontal plane, we wouldn't care about gravity, right? So read the problem very carefully. This one says vertical, so in that case, gravity and the weight of it is affecting the problem. And again, we have force P. Knowing that at the instance shown, the plate has an angular velocity of 20 radians per second, so omega is 20 radians per second, and an angular acceleration of 30. So alpha is 30 radians per second squared. Both are counterclockwise. Determine the force P. So find P. And then the components of reaction at A. So find P, AX, and AY. And we know it's AX and AY because it's a pin. All right, so next, I always write my equations. So for this, we know, so this thing is rotating. Anytime I see something rotating, I know that I'm probably going to look at normal and tangential acceleration. So I can say AT is equal to R alpha. It's from point A. So everything is rotating about point A. So that's where this one is actually really interesting. It's not rotating about its centroid. And so we'll see what that causes. So our normal is equal to R times omega squared. For this one here, so he's going to give you your equations for I values, but you know this thing is rotating, so you know you're going to have I. So I is 1 over 12 m times b squared plus c squared. So that's one length times the other length squared, right? So I got this equation from the back of the textbook. So I went ahead and just solved for the I. So you get I is equal to, so you have 1 over 12 times the mass, which is 0.37. I said that b squared, so don't forget to convert all of these to feet since they're in inches. So it would be 1 over 12 times 0.37, and then you have, what is that, 10 over 12 squared plus 20 over 12 squared. So you get I is 0.1078. And our units are pounds second squared times feet. So I just wanted to get that thing out of the way. So now that we did that, let's look at our FBD, and our KD. So for our free body diagram, we know it's rotating about point A. So I have AX, I have AY. I know that the weight, oh, my drawing is pretty bad. This should be centered. I have the weight applied at the center, and then I have the force P at that top corner. So this and this are both 5. I know that the distance from W to the end is equal to 10, and I know that this distance is 4, therefore this distance is 6. And then I have to equate this to my kinetic diagram. So for the kinetic one, I'm going to apply everything to the centroid. So at the centroid, I'm going to have, so we know it's rotating about point A, right? So here's my point A. So I have MAT, so tangential acceleration. And then right there, I have normal acceleration. And then I'm going to have my I alpha. And so now it's just a matter of our equations of equilibrium. So we're going to equate the forces that are occurring on this to this side. And we're going to equate the moment on this side to this side. And that's all we do. So now if I do sum of moments about point A, so AY and AX are 0 since they're at that point. I'm going to have negative W times 6 over 12 since I have to convert it to feet. Then I'm going to have P, which is positive, times 20 minus 4, so 16 divided by 12. And this is going to equal, so on this side, MAN, that goes towards the center, so that's 0. Then I have M times the tangential acceleration, so I have MAT times 6 over 12, and that's positive, what? This right here is 6 inches, the distance from the centroid to point A. And then I also have plus I alpha. And for this one, I already said that tangential acceleration is equal to r times alpha. The r for that is just 6 over 12 again. So essentially, this here can be written as m times 6 over 12 squared times alpha. So all I did was plug in r alpha for my tangential acceleration. So I know what the weight is. The weight is 12. I don't know P, but I do know alpha, right? Alpha is equal to 30. So from this equation, we get P is equal to 9.0225. Good? So once we get that, we can do our sum of forces in the x direction is equal to sum of forces in the x effective. So looking at my free body diagram, oh, I just noticed that should be AY and that's AX. I don't know why I did that. Anyway, so we have AX, that's the only thing in the x direction. So if I look at my kinetic diagram, I'm going to say AX is equal to negative m times AN. My normal acceleration is equal to r omega squared. So from this, I say AX is equal to negative m times r omega squared. Sure, sorry. So AX is negative 0.37 times the radius, which is 6 over 12 again, and then omega, which was 20. So AX is negative 74.5. All the negative sign means is that my assumed direction was wrong. That's it. Now I can do sum of forces in y is equal to sum of forces in y effective. So looking at my free body diagram, I have AY minus the weight, which is 12, plus P, which is 9.0225, and that's it. And that will equal my mass times my tangential acceleration. We already said that AT was equal to R alpha, so I'm just going to plug that in there. So R was 6/12, alpha was 30, my mass was 0.37. So solving for AY, you get 8.57. And so that's all you do. So stepwise for these, do your free body diagram, your kinetic diagram. Be very careful with your distances for it. This one got a little confusing, so just make sure that you know where it's rotating about. And then it's just your EOE. So these problems are very similar to statics. The only difference is you equate it to the kinetic diagram. That's it. You guys ready to move on to chapter 18? All right, so this will be the last one we get to. So we aren't going to go over this one here, but this one is, again, in my solutions. Chapter 18, I know, is your favorite, right? So we're going to go over this thing. It says, a thin rectangular plate of weight 15 pounds. So I know W is 15 pounds. So my mass is 15 divided by 32.2, which is 0.4658 pounds second squared per feet. Rotates about its vertical diagonal AB, so it's rotating about AB with an angular velocity of omega. Knowing that the z-axis is perpendicular to the plate, so we're only looking at the xy axis, and that omega is constant. So if we have constant omega, what does that mean about alpha? 0. So omega is 5 radians per second in the j direction. Determine the angular momentum of the plate about its mass center g. So we need to find hg, and then we also need to find the kinetic energy T. So for this one, we're going to use principal axes. And so the real thing with, like, yeah. I mean, I'm going to use J. Yeah, so you could just say that omega y is equal to 5. Or omega y, like, yeah, I would just leave that as like omega y. And you'll see why in a minute. So for our equations, we know that hg, so the angular momentum about its center, if I'm using principal axes, will equal ix prime omega x prime I plus I y prime omega y prime j plus I z prime omega z prime k. Right? So this is, the primes mean, like, we're going to break it down based off its geometry. Then I know that the kinetic energy is 1/2, and then I have I x prime omega x prime squared, I y prime omega y prime squared plus I z prime omega z prime squared. So a very similar equation to what we're used to. So now that I have the equations written, I'm going to do my free body diagram. And so this is where I'm going to try to be very careful with this. So here are our standard x, y axes. And we know that this thing, I'm going to do my best to draw this. I kind of missed. I was trying to get it right at its center, but just pretend that this is drawn properly. Okay? And so what I'm going to do is I want to flip this based off its geometry. So I'm going to say that this line right here that runs through the center is my x prime axis. And then this point right here is my y prime axis. So these are our principal axes. And so what I can do is I'm going to try to convert. So we know that our omega is in the y-axis, but we want it in our principal axes. So I know that this omega here, I have to break this down into components on the other axis system. So we're converting it. So you see here from geometry, so if I draw a line through that, this is 9, that's 12. If you were to solve for this, like, do you guys see that that's a 3, 4, 5 triangle? Okay. So this here is 3, and that's 4. So 3, 4, 5. So what I'm going to say then is, so now I need to convert that omega to x prime, y prime, z prime. So omega x prime is going to be 4 over 5 times omega y. You guys see it? So the omega y, that's my hypotenuse, so we're just using similar triangles. Then omega y prime will be 3 over 5 times omega y. So plugging in 5 for omega, you get 4 radians per second and then 3 radians per second. Since for this one we're told that z is acting perpendicularly, we can say that omega z prime is equal to 0. So we don't even care about it. So we can actually come back up here and simplify our equations. So I don't care about that component, and I don't care about that component. Good? So we also need to find our ix prime and our iy prime for this problem. So find omegas, find I. So once again, I always write my equations first, then I find everything that I need to plug into those equations. So for I, x prime, so I'm looking at the rotation about the x prime axis. I'm going to have 1 over 12 times the mass, which is 0.4658. And then I'm going to have times the height of it, so the y component. So this here was 9, right? And so I want to convert that to feet. So 9 over 12 gives me 0.75 feet. And then if I look at this component here, that's 12. So that's just 1 foot. Everyone good with that? That's because my mass is in pounds second squared over feet. So that's a really common error, is that people will just plug in inches, but you need feet for it. So this is times 0.75 squared. That gives me 0.022 pounds second squared feet. Then my iy prime will be 1 over 12 times the mass. And then I'm going to look at, so remember, if we're looking at the rotation about the y-axis, we're going to look at an x distance. So remember, it's moment of inertia. So whenever you think moment, think perpendicular. So I'm going to have times 1 squared. That gives me 0.039 feet second squared, pound, whatever it works. So now we're just going to plug that into our equation. So I can say Hg is equal to, so my ix prime, which is 0.022, times my omega x prime, which is 4. But this is in the I prime direction, or the x prime direction. This is not in the standard xy axis, so we're going to have to convert these back. Then I have plus 0.039 times 3 and the j prime. This gives me 0.0873 I prime plus 0.1165 j prime. And that's in pound-feet seconds. So my little trick for this is to convert omega x prime into the, or to convert omega y into the x prime axis, we multiplied it by 4/5. To convert it back, we're essentially going to multiply it by the opposite, or 3/5. That's my little trick. If you want to get into the geometry of it, then I would suggest that you just practice it and play around with the triangles and how they break down. But I would use the trick for now. So I can say that I prime, so I'm going to plug in components for it, is going to be 3/5i plus 4/5j. Okay? So essentially what you have is this triangle here. If I were to draw these lines that are perpendicular to my x and y axes, then this is 3, this is 4, this is 5. That's the same on the y. So my j prime will be negative 4/5i plus 3/5j. So do you guys see how if I were to draw this on this one here, this is 5, this is 4, that component is 3. Okay? So essentially it's like flipping them. And so that's how I came up with those components in the sign. So I would have you just check those. Then what you will do is you're going to take this I prime, this j prime, and you're going to plug it in. So you're going to take this, plug it in there, take this, plug it in there. That will convert this back into your standard xy axes. So then you get hg is equal to negative 0.0408 in the I plus 0.1398 in the j. And that is in pound-feet seconds. And then I apparently forgot to do the kinetic energy for this one, but all you have to do for that is just plug it back into the one equation. So I don't have an answer for that, but T will just equal 1/2 times your I x prime, which was 0.022, times your omega x prime, which was 4, that's squared, plus 1/2 times 0.039 times omega y prime, which is 3 squared. And that should give you the answer for that one. I don't know how I didn't do that. Any questions about this problem? I know I don't have an answer to give you for that, but that's how you do it. You guys good? Would you like to go back and revisit the one that we skipped from chapter 17 and just look at the steps for it before we go? Okay. So for chapter 17, so for this problem, the real thing that I wanted to point out for this, so this problem says you have a 45-pound uniform cylindrical roller. Initially at rest, it's acted upon by a 20-pound force, pulling it from its center. Knowing that it rotates without slipping, find the velocity at its center g after it's moved 5 feet and the frictional force required to prevent slipping. So what you do is I use energy for this, but before that, I drew a free body diagram and kinetic diagram. Where is it? So just a fun fact for you guys, I don't know if you learned this from the videos this semester, but if you have something that's rolling without slipping, then the instantaneous center is going to be at the contact point or at the ground, which makes sense, right? So if that point isn't like shooting out from under itself, so imagine if you have like a car and it's like spinning out, it's not going anywhere, right? So it's slipping. There's a velocity at the bottom. But if it were to actually be moving, it's essentially as if it gets stuck and then it kind of like the whole car moves and there's no slippage. So that's kind of how that works. I just thought that was interesting. So for this one, it's like the chapter 16 one. You draw your free body diagram, you draw your kinetic diagram. I used work energy for this one. Just note that friction does not contribute to the work. The only thing that contributes to the work is the force that's pulling it. So initially it's at rest. For the final, you're going to have the translation plus the rotational kinetic energy. So that equation is 1/2 mv bar squared plus 1/2 I omega squared. Essentially just plug it in and solve for V. So for this one, the real thing to take note of is omega is going to equal V divided by R. You know that V is equal to R omega, right? So you just flip the equation around. And that's how you get V. Because this is moving at a constant acceleration, it's not slipping, we can use the kinematic equation. V squared is equal to 2a delta x. You guys remember that one? I think it's V squared equals V naught squared plus 2a delta x, but for this one there's no initial velocity. So from that you can find the acceleration of the centroid. Then from there you can go back and do like what you did in chapter 16 and equate your sum of forces of the free body diagram to the sum of forces on your kinetic diagram. So essentially you would just have the force that's pulling it, which is 20, minus the force of friction is going to equal mass times acceleration. Well, you found the acceleration, you know the force, and that's how you get the frictional force for it. So that one wasn't too bad. I think that's pretty straightforward. Any questions about this? I know we kind of went through it pretty fast. Everyone good? So if there are no other questions, that is all the time we have. If you guys could bring me those surveys that I passed around. Thank you guys, and good luck on the final and all your other final exams this semester.